Just take and give it to more people. Okay, so good morning everyone. First thing I would like to say is, have you seen the mail which I sent yesterday night with the link to the YouTube playlist? So the first lecture which we had recorded on Monday, it's already available. So you can just revise it anytime you want. So even today's video will be there. So let us get started with today's class. So today I would like to talk mainly about one concept or one topic, which is two sources connected with one transmission line, how the power flow happens on that. Okay. That is the small sheet of paper which I have just given, so you can just refer to that, which has the question that we would like to discuss. Of course, I will write it on the board also, so it's fine. However, from the previous lecture, there were some problems which are just left out. So maybe we'll quickly revise one or two of them and then we'll come to today's session. Okay. So if you notice, we had about 7 questions last time which I circulated. So out of 7, I think we only looked at 5 and 2 more we did not lift. 5 or 6. So I think 4th question we did not even touch, and then 7th question is there. So maybe quickly I'll just talk about the 4th question. Of course, I will not solve it full detailedly. I'll just give you the general idea how we can work it. So maybe I'll just explain it on board so that you can just have a look at it. This is the 4th question that was discussed in the previous class. Okay. So the question is like this. There is this is the circuit. This is V and F. So the concept is here the F is variable. That means the frequency can be changed. Frequency of the supply, I can change it. Okay. And this is an impedance. Okay. So first question I'd like to ask is, the value of impedance depends on frequency, yes or no? Yes, it depends on frequency. So impedance is resistance plus J into reactance. Okay. So the resistance, not much depends on the frequency. Strictly speaking, even resistance also changes, but that's a different topic. But the major change you can find in the X with the frequency. Okay. Now the question is, if the frequency increases, reactance also increases. True or false? Yeah. So F increases, X increases if it is inductance. Okay. So where XL is 2 pi FL. Okay. L is the inductance in Henrys, XL is the reactance in ohms, and this 2 pi F is the multiplier which can convert the inductance value into reactance. F increases, X decreases. So this is in the case of capacitance. So Xc equal to 1 by 2 pi Fc. So F and Xc are inversely proportional. So frequency increases, reactance decreases. Okay, so coming to this question. Okay, the question is like this. So experiment number 1, my value of V, F and I. Okay, so I am measuring the current here. So this is I. So V, F, I and Z, these are the variables here. So experiment number 1, 10 volts and 25 hertz. This is in hertz. Then the current was 100 milliamperes. This is in milliamperes. Now experiment number 2, this is 10 volts, 75 hertz, and the current is only 60 milliamperes. Okay. So what has happened in this example is, the voltage is constant, frequency increased 3 times, and the current is decreasing. So can you tell it is Inductance or capacitance? It is inductance. Why? Yeah. Yeah. So I think some of you know the answer. So because the frequency is increasing, XL is increasing. In the case XL is increasing, impedance is increasing. Therefore, current is decreasing. Okay. So if the current, instead of 100, if it is 160 milliamperes, current is increasing, that means you can say it's a capacitor. Okay. You are sure at least up to that. So we can actually calculate now. What? Okay, so the question asked is, what if it's a mixed case? What if this is a RLC triple all three combination? Then it may not be correct. Okay, so then what happens? If I increase frequency, will the impedance increases or decreases? Yeah, it depends on the L and C values. Okay, so maybe you can just try it separately, but then. So it might be something like this. Frequency is increasing, then inductance is increasing, the impedance is increasing. After a while, the frequency is increasing, it is decreasing. So there will be something like this. Low frequency, or I think, I'm sorry, I think this is different. It is like this maybe. Okay. So at one value, the frequency will be minimum, and on the left side and on the right side, it will be increasing. Okay. So you can try this at this point, but at least you can say one thing: where the frequency or where the impedance versus frequency, where the impedance is minimum at this point, what is the reactance? So the reactance will be 0. XL and XC both will cancel each other, and then it will be 0. Okay. So you can check that. Okay. On the right side, the circuit will be inductive. On the left side, the circuit will be capacitive. Is it so? Okay. Coming back to this problem. So can you calculate what is impedance here? What is impedance in the first case? See, we don't have the complex quantity. We just have the magnitude. We don't have the phase. Okay. So just go by magnitude. Z equal to V by I. So 10 divided by 100 milliamperes. How much is that? Okay. So 10 divided by 100 into 10 power minus 3. Okay. So it's all, is it 1? 100. Okay. It is going to be 100. So 100 ohms. Okay. This 100 is what? R square plus X square under root, or 100 square equal to. Okay. So this is the R, we don't know, it's something fixed value. This is the X at the time when frequency is 25. Okay. At the time when frequency is 75, this will be 3X. Okay, and R will be same. Okay. In that case, what is the impedance? So it will be 166.7 and then square. Okay. So you can just subtract. Then this will be 100 square minus 166.7 square equal to, this will cancel, equal to minus 8x square. Okay. So can you calculate what is x in this case? How much? 47.14. Can somebody verify that? 100 square minus 166 square divided by minus 8. And then square root of that. Just quickly verify that. Okay. So yeah, so looks like this is the correct answer. Then what is R? Okay, 18.19. So 88.19. So you can use this relation, 100 square minus 47.14 square, and then square root of that. So this is also ohms. Okay. So you can actually calculate L also because you know frequency and all. Okay, that is fine. So what is the next part of the question? Experiment number 3, voltage is 10 and the frequency is 50 hertz. Okay. In which case, what is the current? So this is the question. In the case when frequency is 50 hertz, what will be the impedance? Impedance will be R square plus 2x whole square, because the frequency will be double that of what it was at x. Okay. So maybe I'll just write it. Let x is reactance at 25 hertz. So in this case, I know R and I know x, that is 88.19 square plus 2 into 47.14 whole square, and then under root. So this will be my new impedance. How much will it be? Okay, 128.9. Have you already calculated it? Cool. So let's write it 129, just rounding off. And then in that case, what will be I? V by Z. So 10. So it's not 100. 10 divided by 129. How much will that be? 77 milliamperes. So it is less than 100 and more than 60. Okay, like that. But is it the average of 160? It's not average of 160. It's not linear. So something slightly different. So these are RMS values. When somebody says the voltage is 10 volts, that means it is RMS value. That means at one point of time it will become 10 into root 2 also. Okay, like that. However, in this example, even if you consider them as peak, there is no difference. Just it's only proportional. Okay, so that is about problem 4. In fact, we were asking what is P and Q also. Active power and reactive power consumed by the load. So since you have all the quantities, active power is I square into R. Okay, I know the magnitude of I, I know the value of R. In each of these three cases, I can calculate it. Similarly, Q is what? I square into X, reactive power. So I know the magnitude of I can square it, and I know the value of X, and I can find out the reactive power. Okay, in all these three cases, it's just calculation. Okay, so is that fine? That was about fourth problem. Okay. Sorry. Okay, now before we move on, just we'll summarize summarize this. I don't know how many of you are carrying this last time, whatever the paper I've given, questions. So let's just remember, or let's just revise. Okay, so what are the things that you learnt from these problems, just for review? Okay, polar form to rectangular form to phasor form. So how to, if one is given, how to convert to the other. This is very, very important step in any AC circuit. This is for AC quantities, AC quantity. So maybe AC current or AC voltage. If somebody is given the value in rectangular form, you can convert to polar or phasor or whatever. Okay, what else you learned? Yeah, if you had seen the power triangle, voltage triangle, and impedance triangle. Okay. What else? Just now, yes, just now we saw that relation of F and impedance. Okay. What else? So we solved one problem on power factor correction or improvement, and we have seen something about P and Q and S, active power, reactive power and apparent power, what are the units and so on. Okay, so P is in watts, Q is in vars, and then S is in VAs, volt amperes. So these are the units. Okay, you can use kilowatt, kilovar or kVA or megawatts, megavar and MVA. What else? Okay, so yeah, so there was one problem which was about iron losses, copper losses in a coil. Okay. So whether it is iron loss or whether it is copper loss, you can model it in the form of, in fact, copper loss is right away because of the resistance of the copper wire, whereas the iron loss is because of the heating of the core, which you can also model in the form of an effective resistance in the circuit, and you can solve that. That's what we have seen from one of the problems. So there was one question about two sources connected by one impedance. Sixth question that we'll see in more detail today. Okay, and the last one is about. Okay, let's do the last one. Since we are anyway operating with complex numbers, very in at least in the AC circuit analysis, very important and useful complex number. It is called A. Okay, so A equal to 1 angle 120 degrees. Okay, the magnitude of A is 1 and the phase of A is 120 degrees. What? Yes. So it's A is a constant. It's just like that. One angle 120. It's A is a constant. Okay. What are its properties is what is interesting. Okay. The question is it amperes or volts? So it is nothing. It is just a multiplier. It's a unit. So suppose if I take a voltage. Okay. So 100 sine omega t plus 20 degrees volts. Okay. I take a voltage like this, and if I multiply V into A, what happens? This is what is the question we are asking. Okay. So if you represent V in polar form, what will it be? Will be 100 by root 2. This is the RMS value of the magnitude of the voltage, and the angle will be 20 degrees. Okay. So what is 100 by root 2? It is 70.7. Okay, these are just, so this is my V. Now what is V into A? Because magnitude of A is 1, anything multiplies with A, its value will not change. It is same 70.17 and the angle will be 20 plus 120 and it will be 70.7 140 degrees. Okay. The same thing I will write it in the form of vector diagram or phasor diagram. This is 100 and the angle is 20 degrees. Now if I multiply it with A, I will just draw a circle like this. So it will go like this somewhere. So this total is 140 degrees. So multiplication with A is nothing but rotation by 120 degrees. Okay. We also have another interesting constant which is J, which is 1 angle 90 degrees. Okay. So you multiply anything with J, it rotates by 90 degrees. So V into I, okay, will be 70.7, angle will be 20 plus 90, it will be 110 degrees. Okay. So it will be something like this. So the length will be same, just, and this one is 90 degrees. Okay. You rotate anything 90 degrees. Okay. Now let's come to what is there in this. So a phasor A is represented A equal to 1 angle 120. Find the following. Find A square. Okay, what is A square? So 1 angle 240. Okay, so you don't have to worry much about how it is. Just you multiply in polar form, angles will add. What is A cube? 1 angle 360 degrees, which is also equal to 1 angle 0 degrees. Okay, What is a to the power of 4? Is nothing but a cube into a, is nothing but, see this 1 angle 0 is nothing but just 1 only, it is nothing but a. This is actually 1 because imaginary part is not there. What is 1 plus a square? So what you do is, this is a, okay, this is a square and this is a cube or 1, okay. What is 1 plus a square? So a square is here, just add 1 to it. Okay, so you will get something like this. It turns out that the exact opposite of this will be here. Okay, it will be like 1 plus a square will be minus a. Okay. So in other words, let's look at it like this. Okay. So see, I want to find a plus a square plus a cube. I want to find the sum of all three. This is nothing but 1. I want to find what is 1 plus a square. Okay. So 1 is like this, a is like this, a square is like this. So I reach the origin point. So 1 plus a square plus a, or 1 plus a square. Okay. So 1 plus a square is 0. Vector addition. Okay. So therefore, what is 1 plus a square? So this you go that side, it will be minus a. Okay, something like that. So what is 1 minus a square? This is something different. What is 1 minus a square? So here you should this is 1, okay, this is a square, this is minus a square, okay. So this is a parallelogram kind of thing now. This is 1 minus a square, okay. So this is 1 unit, this is 1 unit, this is total is 60 degrees because this is 120 degrees. So this is minus a square, so 180 minus 120, this total angle will be 60 degrees and this angle will be 30 degrees and 30 degrees. So any parallelogram, or this is actually a, I think it's called rhombus in mathematics. So 1, 1, 1, 1, all our 4 sides are equal and the angle is 60 degrees, 60 degrees, and here it is 120, 120. Okay. In that case, if you just solve it, it will be root 3 length. Okay. The length of this will be root 3. Okay, and the angle will be minus 30. You can just solve it. I am not, just to save time, I am not doing that. Okay. Or you can do something like this. You can simply, convert. See, our objective is to find 1 minus a square. Okay, this is 1 plus j0. This is, you can convert to polar. So a square is 240 degrees. Convert into rectangular and then add the real components. All these things, you will find that the length will be root 3 units and the angle will be minus 30. So in other words, I will write it 1 minus a square equal to root 3 minus 30 degrees. Okay. So this will be useful when you are going for 3-phase circuits. Right now you don't worry about it, just to observation, that's all. Okay. So what is A inverse? What is 1 by A? So if you multiply by A, you will rotate by 120 degrees in one direction. If you divide by A, you will go back by 120 degrees. Okay. So what is 1 by J? This is nothing but minus J. So similarly, 1 by A is nothing but minus A. Okay. So you are rotating back by, oh, I don't think this is correct. This one is correct, na? Minus A square. Yeah, so going back one time is equal to going forward 2 times rotation. Okay. Yeah, this is correct. 1 by A is A square. So therefore A cube is 1. Okay. And 1 by A square is A. So all these things. So all these things will become intuitive if you think about A as a phasor. Okay. So that was the concept that I wanted to show in this one about okay, or I'll say behavior of A equal to 1 angle 120 degrees. Okay, how it behaves. So we'll just leave this now. Let's come to a new topic today that we'll discuss. Okay. Okay, just for you to read, I have given a small piece of paper. You might be having it. So in which on the left side of the paper there is one DC example. So I'll just start explanation by that. So only one I have. Okay, so what is a DC case? So of course the idea is two voltage sources connected by one transmission line, how it works. Okay, very simple circuit I have. It is like this. 100 ohms, sorry, this is how much? 10 ohms. This is my load resistance. And this is R, which is 1 ohm. And this is 100 volts, and this is variable. And plus minus 10 volts. And this is also 100 volts. This is fixed. This is called V2. This is called V1. Okay. So what I am trying to do is, I'll take V1. V2 I'll fix it. 100, 100, 100 like this. 1, 2, 3, 4, 5. Okay. Let's do 5 experiments or calculations. 1, 2, 3, 4, 5. Now in each case I want to find out I. In each case I want to find out I square R. That is losses. Okay, and in each case I want to find out IL square RL. Okay, this is IL. Okay. For that, of course, you need what is IL. Okay. So units, this is in volts, this is in volts, this is in amperes, this is in watts, this is in watts, and this is in amperes. Okay. Because this is DC circuit, very easy, so not a problem at all. Let's start with this case. Okay. The case 3, where both these voltages are equal. Okay. So my question is, what is this I square IL first of all? What is IL? So because this is a voltage fixed 100 and then immediately it is 10 ohms. So IL is always fixed. Irrespective of value of V1, always IL is fixed. Okay. How much is IL? 10 amperes. Okay. 10, 10, 10, 10, 10. Okay. Variations of V1 does not affect the IL. It keeps on varying. It remains fixed. Okay. And therefore, what is I square, IL square into RL? So this will be 10 square into 10. So this will be 1000 watts. Okay. This is in watts. So, or 1 kilowatt you can say. Okay, that is my, what is it, IL. So, sorry, the load power. Okay. Now, I will define two more quantities, which is P1 and P2. Okay. P1 is the power supplied by source 1. P2 is the power supplied by source 2. Okay. So what you will notice is P1 plus P2 is not only equal to this 1000, but 1000 plus the losses. Some losses also there. Okay. So 1000 plus losses, you will be P1 plus P2. Okay. So in this case, what is I? I in the line, this one. So I will be 0 because both voltages are same. Ohm's law, this point to this point, it is 0. And therefore, what is I square R? Also it is 0. And what is P1, P2? See, P1 is nothing but V1 into I. So this is nothing but V1 into I. This is nothing but V2 into, not IL, I2. Okay, let's call it I1 and I2. Okay, so this voltage into this current is power here and power here. Okay, what is V1 into I1? It is 0, and this one will be V2 into I2 will be 1000, because I2 itself will be, so this side is always 10. I'll write it here. So if this is 0, then 10 minus 0 is 10. So I2 is 10, like that, sharing of load current. So I hope you are following what is going on here. So slightly I will reduce the V1, or let's go down, let's increase V1. Okay, I want to use 105. Okay, 105 volts at V1. I increase the supply voltage here. Then immediately how much current will flow? So 5 amperes definitely has to flow, because this minus this is 5 volts divided by 1, definitely 5 amperes is flowing. So out of 10 amperes, 5 coming from here, 5 coming from here. Okay. So what is I? I is 5 amperes. This is I1 actually. So 5 amperes. What is I1 into R? So 5 square into 1, 25 watts. Okay, 25 watts is lost as power. Therefore, what will be my V1 into I1? That is 100 into 5. So, sorry, yeah, it is 105. So 105 into 5. How much is that? 525. Okay. So V1 is 105 and then I1 is 5. So V1 I1 is 1. This multiplication of these two, 525. Okay. And then this one is 500, because 100 volts into 5 amperes, this one. So total is 1025, 1000 is going here, 25 is lost. Okay. So just you are slowly starting to understand some point here. Now 110, okay, if I use 110, entire 10 amperes comes from here, and what will be the I square R losses? 100 watts is lost here, because 10 square into 1, and V1 I1 will be 1100. Okay, and then this one will be 0. There is no power sharing on the second one. Okay. So you are arranging the voltage in such a way that by the time the current reaches here, the whole current is supplied from this side only, and I2 will not be there. Okay. So reverse happens if this is 95. So you will notice that now the load current does not even come into picture. If this is 95, the power starts flowing in reverse direction and all that. Okay. So still the current, I'll write it minus 5, whereas I square R, because square is there, the minus will get cancelled, and this still will be 25 watts will be lost. And what will be the V1 into I1? It will be minus 25. That means the source 1 is receiving the power. Okay. How much? Yeah, 95 into 5, sorry. Yeah, minus 475, sorry. Minus 475. That means it is receiving 475 watts. That means this may be charging or something. Okay. And then what is P2? It will be 1500, because 100 into 10 plus 5, 15. 100 into 15, 1500. So out of 1500, 1000 is going to the right side, 500 is going to the left side, 25 is getting lost, remaining 475 is delivered to source 1. Okay. So that's how this is working. Okay. So similarly, in this case, if the voltage was 90, then the current will be minus 10 amperes, and this one will be 100 watts will be lost, and this will be how much? So V1 90 into this one minus 900, and this will be how much? 2000 watts. Okay. So what do you understand from this? You can control the power flow between two places by controlling the voltage magnitude in the case of DC circuits. Okay. Uh, Now I'll just give you one more additional information. Okay, so the cost of power generation. Okay, so for source one, uh, for uh, for 1 watt, the cost is, let's say, for generating 1 watt, the cost is, let's say, 3 pies. For source 2, for generating 1 watt, the cost is, let's say, 4 pies. Okay, and there are losses involved. Okay, there is a losses also going on here. Okay, so the question is, what is V1 so that load power, P load, equal to 1000 watts is met with least cost. Okay. I want to meet this demand here. I cannot use V2 completely because V2 is costly. But then I cannot use V1 completely. Of course, it depends on the values. So we'll just manipulate these values if the answer is not coming properly. Okay, so let's just calculate that. So I'll write it C1, C2. Okay. C1 is cost of generator 1 and C2 is cost of power generator 2. In all these cases, we are definitely meeting the demand. Okay. So only question is, what is the total cost? Okay. What is the total cost in this case? In the third case? So 0 plus 4000. So total cost is 4000 paisa or 40 rupees. Okay. I wanted to write PS. Okay. So in the we'll just go one value down. Obviously we cannot go up because we are actually consuming power. So if I go down, in this case 500 into 4, which is how much? 2000 paisa. In which in here 525 into 3, how much? 1575, and the addition of this will be 3575. Obviously this is cheaper. This option is cheaper. Looks like we can use more power generation from V1 because it's cheaper. So let's look at this case. 3300 and this one is 0, 3300. Okay. So looks like we actually have to increase more. So we don't even have to generate any power at V2. Okay. So of course our this choice was not proper. So it is like that. So if you make it slightly more costlier, just like 3.1 paisa, okay, then let's calculate once again. Okay, if it is 3.1 paisa, how much will this be? This will be 3100. Okay, and how much this will be? So this will be same 1575. This will be 1550. Then if I add them, 3175 or 3125. Okay. So you suddenly see the cost is increasing. 75. This is 75, na? Is this 75 or 25? So in that case, this should be 25, 3125. See, the cost is increasing. Okay, I don't even have to calculate the next step. So the cost is increasing. So you can still try 101, 102, 103, and then you will notice that at one point it will be at what point it will be cheaper. So something like this keeps on happening in power systems also, where you have many generators and many loads, and then you are trying to use the cheapest generator and trying to generate and meet the demand. So this was DC case. So without spending more time on this, let's look at the AC case, which is which is nicely more complicated. Okay. So this is about DC case. So now you can actually create a Microsoft Excel document or whatever. In that you type these numbers, put the equations, try the value of V, and then find out the total cost and make some plots and all these things. You can try it instead of calculating each and every individual step. You can write it in a Excel sheet and try to play with it. Okay? You try that. I'm just suggesting it. So you notice that a circuit as simple as this has so much meaning inside it, so much concept behind it. So now come to the AC case of AC sources. So here I am not showing any load. So there is no load here, just for ease of calculation. You can just assume that one is supplying, other is consuming. Okay, so how it is. So this is E1 and the phase is delta 1, and this is E2 and the phase is delta 2, and this is R plus Jx, which is nothing but Z. Okay. So usually a power transmission line will be inductive because it does not have, compared to capacitance, the inductance will be more, so it is plus Jx. So let's solve the first problem. So E1 delta 1, E2 delta 2. So this is given as 100 or 50 angle 10 degrees and then 50 angle 0 degrees. Now the question we are asking is how much is the power, active power, reactive power flowing in this circuit. Okay. So I want to find out what is P1, what is Q1, P2, Q2. Okay. Now what is also P line or P loss, P plus JQ loss. I'm just writing loss, P loss and Q loss. Okay. So this value is 0 plus J5 ohms. That means the resistance is neglected, only the reactance is 5 ohms. Okay. So how will you start working on this? First is you find the I. Okay. So what is I? I is E1 delta 1 minus E2 delta 2 divided by Z. Okay. So that is now 50 0 degrees or 10 degrees minus 50 0 degrees divided by J5. Okay. So now you need to take out your calculators and calculate. Okay. So as I already told you, there's so many calculations like this you will have to do, so a calculator is a must. How would you do it? If it is a subtraction of two polar numbers, you convert both into rectangular, subtract the thing, and then convert back into polar and then divide by 5 angle 90. So I'll wait for you to tell me the answer. See, although it's a direct step, I'll try to write down some of the intermediate steps, but that's not required. You calculate directly. I just expanded it. So if I convert this into rectangular form, I'll get it like this. So I hope you know this. That's what we taught last time. Okay. So if there is this is 50, angle is 10 degrees, x-axis component will be 50 cos 10 and the y-axis component will be 50 sin 10, and then just to indicate that it is y-axis I am putting j. So multiplying by j rotates by 90 degrees. 1.743 5 degrees. Okay. So somebody has calculated and then gave the answer finally to be like this. Okay. So if that is the case, this is I. Okay. Now what is S1? S1 is P1 plus J Q1. Okay. Complex power supplied by source 1. Okay. P1 plus J Q1, which will be V1 I, because it's I or I1, everything is same. I'm just putting I, but you should put a conjugate. Okay. So for finding the complex power, you need to do the conjugate of I1. So what is the meaning of conjugate? Conjugate means the imaginary part you reverse the sign. Okay. If the imaginary part or the angle you reverse it. Okay. So 1.743 5 degrees, then that means I conjugate will have minus 5 degrees. So that's the conjugate operator. Okay. So why you have to do conjugate? So if you multiply directly, it will add the angles. But see, if I'll just give you an example. Let's say voltage is 100 angle 10 degrees and current is 5 angle 20 degrees. Okay, not 20. I'll use 30. Okay. Now, what is the angle between voltage and current? So if I want to find out the relative angle between these two, I have to subtract one from the other. Okay. So subtract 30 and 10. So one is at 10 degrees, other is at 30 degrees. So the difference is 20 degrees. Okay. And if you want to find out the power, Vi cos phi. Okay. So what is this cos phi? Phi is the angle between these two. Okay. So you cannot just simply multiply V and I and then cos of addition of the angles. You have to take the difference of the angles. So for taking the difference, I am putting conjugate on I. Okay, so this is a different example. I'll just take it, remove it. So can you do that now? What is V1? 50 10 degrees multiplied by 1.743 minus 5 degrees. How much is this? 87 14. Let's round it to 5 degrees. Okay. So can you again split it into P1 and Q1? What is individually P1 and Q1? .86.8 and what is Q1? 7 point? 7.6. Okay, so I'll write it here, 86.8 plus J 7.6. Okay, now it is very important, just pay attention here, it's very important to know what exactly it is. I'm just writing supplied. Okay, that means the first source S1, that is supplying 86.8 watts and supplying 7.6 watts. Okay, why I am saying supplying? Okay, you just notice this part of the circuit. Okay, the current is leaving the this terminal. So if I take these two terminals A and B, the current is leaving this and the voltage is E1. Okay, so and then I am just taking E1 into I star. Okay, that means the concept is supplied. Okay. In the case here, what happens? See, what is S2? S2 is E2 into I2 conjugate. Okay, but then look at the direction. The current is entering. So this is the positive side, this is the negative side of this AC, and the current is entering into this. Okay, so here it is received. Okay, so the power is received at the receiving end. Okay, but then we'll see what values we get here. Okay, so what is E2 into I2? 50 angle 0 degrees multiplied by 1.743 angle minus 5 degrees. Okay, so how much is this? 87.14 angle is minus 5 degrees. Okay, so you notice these two are, this is plus 5 whereas this is minus 5. Okay, so when you convert it, what will happen? 86.8 minus J 7.6. Okay, but then because of our direction, here I am saying received. Okay, now again notice here, those who are not looking at the board, just concentrate. Why it is received? Because of the current direction entering into the positive terminal of this one. So I want to make it received and then I'll say supplied. That means this minus will become plus, this plus will become minus. Okay, so I want to describe the circuit in such a way that both sources are supplying the power. Okay, so whereas the second source is supplying minus 86.3, that means actually it is receiving 86.8 watts of power, but then I want to use the terminology both are supplying. Okay, so where is this active power going? 86.816 supplied from here, minus 86, therefore the active power just gets cancelled. Okay. So active power loss is 0. So there is no active power loss, because also you notice the resistance is 0. Okay. What happens to the reactive loss? So this will be J 15.2. Okay. Now that is by addition, like you are doing here, but then can we verify that? How do you verify the power here? Simply do I square into Z. Okay. So when you do I square, strictly speaking, you will not do I square, you will do I into I conjugate. Okay. So one angle will be plus, other angle will be minus, so it gets cancelled out. So only you are worried about the magnitude of I. So magnitude of I square multiplied by Z. Okay. So what is magnitude of I square? 1.743 whole square multiplied by J5. Okay. So what is 1.743 square? 1.743 square, slightly more than 3 I should expect. 3.03 multiplied by 5. 15.2, which is equal to this one, so it is kind of verified. Okay. So now to draw the picture, what is happening? So I use, so this is active power. So active power starts from here and then comes here, 86.8 watts. Okay. So this is the power transfer, whereas reactive power and then like this. So here it is lost. I'll just draw like this. 15.6, 15.2 J, 7.6 coming from J 7.6 coming from here, J 7.6 coming from here. I don't know how visible this is. Okay. Now, in the previous DC example, how to control the power flow on this line? In the case of DC, change the E1 value. Okay, but look at the E1 value here. E1 value magnitude is same. So even though the magnitude is same, what is happening? The power is still flowing from here to here because of the angles. Okay, so the angle determines the power flow. Okay. So in the question which I given, let's do the second example, case 2. Okay, what is case 2? The entire data is same except that this angle is reversed. Okay, so I'm saying this one is minus 10. This is case 2. Okay, so repeat the whole problem with delta 1 is minus 10 degrees. Okay, then what happens? Okay, so let's try to check here. If this is minus, then this whole thing might change. How it will change, we have to verify. So here what happens? This is minus. Okay, this is minus. So here it will be cos of minus 10. Cos doesn't care. So here it will be sine of minus 10. Maybe this sign will change. Here it will be cos of 0, sine of 0, no change. So now here 90 degrees is there. Okay, so this 90 degrees is actually minus j. Okay, j in the denominator, if you go to the numerator, it will be minus j. Okay, so here the sign of real part is changing. Sorry, the sign of imaginary part is changing, but actually the sign of imaginary part will not change because the j from below goes up and then multiplies it. Therefore, actually the sign of real part will change. Okay, sign of imaginary part will remain same. So the answer is like this. If you calculate it through your calculator and all, minus here, plus here. That's the change. Okay. So just by reversing the sign of delta, reactive power does not, the reactive power flows remain exactly same, just the active power flow direction is changing. Okay. So this P1 will be like this, P2 will be like this. So here this is minus 10 and here the current is, I don't know what will be the current. Current magnitude will be same. Will the current angle will be different? 170? 1.743? 175. Yeah. So the angle is 175 you are saying. So finally you will be getting like this. Okay. So basically source 1 is receiving 86.8 watts and source 2 is supplying 86.8 watts considering the sign. Okay. So if I want to summarize it, in DC, power flows from high V to low V. Okay. So whereas in AC, power, I am writing active power. Active power from high phase angle to low phase angle. Now it is very easy to control the magnitude of voltage in the case of DC, but it is quite difficult to control the phase angle in a AC circuit. So that's why it is slightly complicated to control the power in an AC network. We will come to that when we are talking about AC power networks. This is one observation. Okay, let's do some more observations about the reactive power. Okay, what is the sharing of the reactive power? Total reactive power demand is 15.2 watts. Okay, The 15.2 VARs is a reactive power demand which is shared equally between source 1 and source 2. Why the voltage, why the reactive power is being shared equally? So because the voltage magnitudes are equal. Okay, so let's look at the case 3 in our sheet. Okay, so what is case 3? So everything is same. I'll go back to plus 10 degrees and just I'll change this to 40. Okay, so case 3 I am just changing the magnitude to 40. Okay, now we need to solve it. Okay, so I just remove all this and then I'll remove all this. So solve the case 3 with these values. 40 angle 10 degrees minus 50 angle 0 degrees divided by 5 angle 90 degrees. So this is my I. So first job is to find what is I. So someone can find I. Okay, we got some answer. How much is it? 2.53 angle 56.7. And what is this one? 1.388 plus 2.12. I'm worried a little bit. Correct? I'll just wait for some more people to confirm the answer. Please check the answer. I'm a bit worried about this angle. Correct? Okay. So let's move forward and find out these two. So what is S1? V1 into I1 conjugate. Okay. That is 40 angle 10 into 2.53 angle minus 56.7. I have just changed the sign. Okay. How much is this? 101.6. So again you divide into two parts. Okay, 69.228. Okay, 69.3 I'll write it. 73.98. Okay, so I'll make it J74. Okay, so I'm writing it here 69.3 minus J74. Okay, so just notice here now, people are calculating, you can just stop for a while. P1 is positive, that means it is supplying. So source 1 is supplying 69.3, at the same time source 1 is consuming 74 watts of reactive power. Okay, the same source at the same time, on one hand it can supply active power and it can also consume reactive power, it is possible. Okay. The active power direction, reactive power direction can be reversed at the same time in the same place. Okay, that's what we are just seeing here. What about the second case? What is S2? S2 is E2 into I2 star. Okay, the same thing. How much is that? 69 point. So it should be actually 69.3. It should be, I'll write it 69.3. So because I want to write it supplied, I have to change the sign of all of this. Okay. So what is it? It is minus 69.3. And what about here? Plus J 105. Okay. 105.9. So let's make it 106. Okay. So what you notice is the second source is receiving plus 69.3 watts. So this is 0 because there is no losses. Whereas the supplying part, it is supplying 106 watts. Okay. Out of 106 supplied, 74 is received at the source 1. Therefore, the remaining must be consumed at the line itself. Okay. So we will verify that. So what is the difference? 106 minus 74, 32 plus J32. Okay. So the Q loss supposed to be J32. Okay. So how to verify that? Just simply do I square, magnitude of I square into Z. Okay. So what is magnitude of I? 2.53 square multiplied by 5J. Okay. 2.53 square into 5. How much is that? 32.87. Okay. So which is almost equal to 32 because of rounding off error. Okay. So we have just verified that. Okay. So now to draw the picture, what is happening? I'll just change this. So maybe I'll just draw it more neatly. So this is E1. This is E2. Okay. So the active power is like this. 69.3. Okay. Because the angle is 40, 10 degrees. Okay. This is 50, 0 degrees. Okay. So this angle is leading this angle. Okay. E1 is leading E2 in terms of phase. Therefore, the power flow direction will be left to right. But that is only for active power flow. Okay. Reactive power flow direction, E2 magnitude is more, E1 magnitude is less, so it will be reverse. Okay. So what is that? So from here, so total starting is 106. 106 watts are starting from here. So here something is consumed. I'll write it, or I'll write it downwards. 32, and the remaining 74 is coming here. Okay. 106 generated here, reactive power, 32 consumed in the line, and 74 is reaching here. Okay. Now we still have 10 more minutes left, but then if I want to summarize it, what did we learn here? So in AC, reactive power flows from high voltage to low voltage. Okay, reactive power flows from high voltage to low voltage. Now, it may be also possible, see, you have noticed when it was 50-50, the sharing was equal and the power lost was here, how much was that in the previous example? 15.2. 15.2 was lost here and equally shared by both sides. Okay. Now instead of 40, if I say only 48 or something like that, only 2 volts difference. If I solve the problem, okay, it may happen that the reactive power flow may be like this. So from the source 1, the reactive power flow is coming like this. Source 2 also reactive power flow is coming like this. Both supplying the reactive power and it is consumed here. However, the sharing is not equal. This may be slightly lesser and this may be slightly more, and then it is lost. So you can try that. You can write a small program, and then in that you can make even magnitude variable, even delta variable. By varying E1 and delta 1, you can find out all this relation. Okay. So in fact, you notice this is not a nice thing to do hand calculation with a calculator. Just like see, at one point you were doing calculations on book and pen and pencil and then using your fingers and all, and then at one point you shifted to calculator. Okay. So now is the time you shift to a computer. Start using a computer, write a small program and then use a loop, and then you can vary even you can vary from 40 to 60, and delta 1 you can vary from -10 degrees to +10 degrees. Okay. And then you can make a plot, okay, something like this. So how many combinations you get here? 40 to 60, about 20 different values of E1. 21 actually, but then let's count it as 20. 20 different values of E1, and then how many is, not 20, yeah, 20. This is also 20, okay. 20 into 20, 400 combinations, okay. You can use for loop or if loop or whatever. For 400 combinations, you can solve the same problem, and then find out x-axis. You can keep delta 1, and then you can write it P1, Q1, whatever. Okay. So what is the variation of delta 1 and P1? Will it be like this? As delta increases, P1 increases. Delta 1, P1. The more delta 1 is there, the more active power you are sending from source 1. Is it like that? You verify it. Okay. What? With E1 fixed. E1 fixed. See what we have written here. In a AC circuit, active power flow from high phase angle to low phase angle. Okay. So this is fixed. Delta 2 is fixed at 0 degrees. So delta 1 is keep on increasing. Maybe -10 to +10. Will P1 keep on increasing? That is a question. Okay. And will it be like a straight line? So you can try that. You can try this combination and then find out how it is. Similarly, what is the other relation? You notice here, in AC, reactive power flows from high voltage to low voltage. You can verify that just by plotting Q1 see if Q1 is positive, that means the supplying reactive power. If Q1 is negative, that means receiving the reactive power. So whatever that Q1 value is, and then this here you can see E1, okay, magnitude of E1, okay. Fix the delta. So delta 1 maybe you fix it to 0 degrees, okay. Delta 1 is 0, delta 2 is 0, so there won't be any much of active power flow flowing. Just vary the magnitude of E1 and then you try to see what happens. So here E1 is fixed maybe at 50 volts, and here you can fix the delta 1 and then find out what is the relation between E1 and delta 1. The more E1 is there, the more Q1 it is supplying. So maybe it's like that. Okay, try to find out that relation. So in our class, we are just selecting one case, two case, three case, and then trying to understand it. But we can have this 400 cases and then try to see how it works. So it's a more complete understanding of that circuit. Okay, so we still have 5 minutes left. So quickly, can you imagine what happens now if there is a resistance? So if you look at case 4, the whole problem is same. I think these two are same, and just that Z will be now 3 plus J5. So there is going to be some power loss also. Okay. So we can calculate it, we can do all these things here, but then here it will be 3 plus J5. Okay. So if we repeat the same problem, it will be something slightly, you can verify that the power sharing, how much is the loss and all these things you can verify. Okay. Now on top of this, you can now add the cost. Okay. The cost of generating E1 power is this much for this much, and then the cost of generating E2 power is this much. And then you can think of some load and then try to see what is the lowest cost generation and all these things. So you try all these combinations. I think you have any questions to ask or anything, any observations on what we did today? So shall I assume that everyone followed what is going on today in the class? So okay, so how do we calculate cost in the case of a AC source? Okay, so reactive power does not require any fuel to be burnt. Okay, so strictly speaking, the cost of a AC power generator mainly question is how much active power it is generating. Okay, however, the reactive power will have some kind of fixed cost associated with it. So because to provide that reactive power, you need to have some the design of the machine will be there to have some reactive power range. Okay, so like that. And the another thing is, if a generator starts generating more reactive power and less active power, that means you are using up the current in the generator, but you are not generating active power. So it will be like getting less efficient operation. Okay. So any generator, of course, it will have some reactive power generation because of the magnetic field it has to generate. But then you try to operate it more at a higher power factor with more active power and less reactive power. So like that. The cost is mainly driven by active power because you are burning fuel to make active power. Whereas in the case of wind generator, we are not even burning any fuel, we are just wherever there is wind, you are extracting power from the wind. Okay. So there the cost concept is completely different again. Okay. So depending there, it is more about investment cost, and then the weather data, how much wind is there in that place throughout a year, whether the wind is constant or whether wind is varying and all this. So the cost calculations are different in that case. Okay, so the question is why we are having three phase. Okay, so maybe next class we are going to talk about three phase, next class on Monday. The reason for going to three phase is I want to transmit power from one place to the other place. The distance may be 200 kilometers or 400 kilometers, long distance. I want to transfer the power. Okay, so the question is how to transfer the power with less weight or less volume of transmission lines to send more power. So it is found that, see here this is one wire and this is another wire, two wires are there. Okay, so two wires are carrying 69.3 watts. Okay, now if I use three wires in three-phase system, okay, so what is the amount of copper increasing? Amount of your wire is increasing. Two wires replaced by three wires. Okay, 50% increase in the amount of transmission line. Okay, but will the increase in the power will be same 50% or will be more than 50%? So it turns out that just by adding a third line, the cost is increasing, the copper is increasing by 50%, but the power flow is increasing by more than 50%. So it is more economical to use three phase compared to one phase, because you can send more power with less material. So how it is, why it is, we'll calculate that next time. Okay, that's the reason why we go for three phase. Then the question is, why not use four phase? Because by putting three lines, I am sending more power. Why not use four phase and then send more power? It turns out that in four phase you are doubling the amount of conductors, but the power in four phase does not go more than double. So again that advantage is lost. So the advantage is at three phase, and the four phase there is no advantage. Okay, but then you can still verify what happens in five phase, six phase and so on. So there are some kind of research works also at multi-phase kind of thing. But three phase is more popular, and since we are anyway just trying to learn the subject, so we'll start with three phase. Yeah.
So like in this case,